Section. Introduction. In recent times, there has been a significant shift in the way question answering (QA) models are built, largely due to the influence of models like ChatGPT. These models are favored in real-world applications for several reasons. Firstly, they allow users to interact in a conversational manner, making it easy to ask follow-up questions. Secondly, these models can generate answers without needing specific fine-tuning for each dataset, while still maintaining the accuracy of models that have been fine-tuned. Lastly, these models can incorporate retrieved pieces of information in both open domain or long document settings, where the provided context is much longer than the context window of the language model. However, creating a conversational QA model that can match the accuracy of top-tier models like GPT-4 remains a significant challenge. In this paper, we introduce ChatQA-70B, a conversational QA model that matches the accuracy of GPT-4. We achieve this through a two-step instruction tuning process, an improved retriever for retrieval augmented generation in conversational QA, and a meticulous data curation process. Our contributions include a two-step instruction tuning method and a dataset curation process that significantly enhances the language model's ability to integrate user-provided or retrieved context for zero-shot conversational QA tasks. We show that our method outperforms regular instruction tuning or RLHF-based methods. For retrieval augmented generation in conversational QA, we demonstrate that fine-tuning state-of-the-art single-turn query retrievers on human-annotated multi-turn QA dataset is as effective as using the top-tier language model-based query rewriting model, GPT 3.5 Turbo. We have built a series of ChatQA models and conducted extensive studies on 10 conversational QA datasets. Our ChatQA-70B model outperforms GPT 3.5 Turbo and GPT-4 in terms of average score, without using any synthetic data from ChatGPT models. We also explore the unanswerable scenario, where the desired answer is not included in the provided or retrieved context. We show that adding a small number of unanswerable samples in instruction tuning can guide the model to generate a cannot answer output when necessary, significantly reducing hallucination. Conversational QA improves user experiences by addressing follow-up questions and can also ask clarification questions from users if necessary, reducing hallucination. Many conversational QA datasets have been introduced, where the models are asked to answer questions based on provided context or documents. The provided context or documents can be text only from various domains, or plain text along with tables. Conversational QA involves retrieval augmented generation in open domain setting, or when the provided documents are longer than the context window of the language model. The dense retrievers are usually trained to retrieve the top K relevant chunks given a single question. In conversational QA, follow-up questions may have insufficient information for retrieval, while feeding them along with the dialogue history can be redundant and lead to suboptimal results. Most previous solutions are query rewriting methods. The latest turn of question is rewritten to be a standalone query without additional information from previous dialogue history, so it can be directly used by retrieval model to retrieve relevant context. Many datasets have been collected to facilitate this line of research, alongside multiple proposed query rewriting methods. Section Summary. The introduction discusses the shift towards building conversational question answering (QA) models that allow users to interact with the models in a conversational manner, generate answers without fine-tuning, and integrate retrieved evidence. The paper introduces ChatQA-70B, a white box conversational QA model with GPT-4 level accuracy, achieved through a two-stage instruction tuning method, an enhanced retriever, and careful data curation. The paper also explores related work in conversational QA, retrieval for multi-turn QA, and conversational query rewriting. Section. Fine-tuning retriever for multi-turn QA. In this study, we're focusing on refining a single query retriever for multi-turn question answering (QA). This involves training the retriever on a high-quality multi-turn dataset, and then testing its ability to answer questions it hasn't seen before, a process known as zero-shot evaluation. We found that this simple method can yield results that are on par with the latest query rewriting models, such as GPT 3.5 Turbo. We're also working on instruction tuning, which is about teaching language models to follow instructions given in natural language. There's been a lot of progress in this area recently, with the development of several high-quality instruction tuning datasets. However, there's been less focus on improving the context awareness of these models for QA tasks. We're proposing a two-stage instruction tuning method to address this. We found that simply adding the top K retrieved chunks for language model fine-tuning doesn't help much for a wide range of conversation QA tasks. Instruction tuning has become a key component in building state-of-the-art dialogue agents, which can handle a wide range of tasks without any prior training. We're proposing a two-stage instruction tuning method for ChatQA. We start with a pre-trained language model, and then apply supervised fine-tuning on a blend of instruction following and dialogue datasets. This gives our model a good ability to follow instructions as a conversational agent. However, its ability to handle context-aware or retrieval-augmented QA is still limited. So, we introduce a second stage, called context-enhanced instruction tuning, which is designed to improve our model's ability to handle context-aware or retrieval-augmented generation in conversational QA. In the first stage, we create a large and comprehensive supervised fine-tuning dataset, which includes a social dialogue dataset, a long-form QA dataset with detailed answers, and several instruction tuning datasets. We also include a private crowdsourced conversational dataset, as well as two public human-written conversation datasets. We unify the structure of all the data in a conversational format, and then apply fine-tuning on a language model. In the second stage, we further enhance the model's conversational QA ability by integrating contextualized QA datasets into the instruction tuning blend. This includes a blend of single-turn QA and conversational QA datasets. In addition to the publicly available datasets, we also create a high-quality document-grounded conversational QA dataset, which we call Human Annotated Con-V-QA. This dataset consists of 7,000 dialogues, each based on a document covering a diverse topic. We instruct an annotator to act as both a curious user asking questions about the document and as an agent providing the answers. We also aim to teach our model to indicate when it can't find an answer within the given context. To do this, we construct scenarios where the answer isn't available, and use the sentence, "Sorry, I cannot find the answer based on the context," as the response for these unanswerable questions. This gives us a good balance of answerable and unanswerable cases. Section Summary. The authors propose a two-stage instruction tuning method for ChatQA. In the first stage, they apply supervised fine-tuning on a blend of instruction following and dialogue datasets to improve the model's capability to follow instructions. In the second stage, called context-enhanced instruction tuning, they integrate contextualized QA datasets to enhance the model's conversational QA capability over a given context. Section: Synthetic Data Generation. We're going to simplify and explain the process of creating synthetic data for a conversational question and answer (QA) dataset using a powerful tool called GPT 3.5 Turbo. This tool is great at following instructions and generating text, which makes it perfect for our task. We're not the first to use synthetic data for conversational QA, but our focus is on creating a medium-sized, high-quality dataset for fine-tuning language learning models, LLMs. The instructions we give to GPT 3.5 Turbo are threefold. 1. To guide the model to provide useful answers. 2. To show examples of conversational QA to indicate the type of data we need. And 3. To provide a document that the model can use to generate conversational QA. We've collected 7,000 documents, each about 1,000 words long, from a wide range of topics. Each document is used to generate one conversational QA sample, resulting in 7,000 multi-turn QA dialogues, with an average of 4.4 turns per dialogue. We call this synthetic Conv-QA. Just like in our human annotated Conv-QA, we've also created 1,500 turns with unanswerable questions in this synthetic dataset. Since we don't have context location annotations for the agent's answer, we create synthetic unanswerable samples from synthetic Conv-QA. We do this by dividing each document into different sections, and only considering it a valid unanswerable sample if there are sections that have a lot of overlap with the agent's answer that can be removed, and the remaining sections have little overlap with the agent's answer. We use a 4-gram recall score to measure overlap, considering a score higher than 0.5 as high overlap, and lower than 0.1 as low overlap. Next, we'll talk about how we train our model. To improve its ability to handle tables and arithmetic calculations, we add the ChatQA dataset. We also include single-turn QA datasets to further enhance the model's QA capabilities. We keep the Stage 1 SFT dataset in the training blend to maintain the model's ability to follow instructions. The training blend for Stage 2 consists of 1. A conversational QA dataset, either human annotated Conv-QA or synthetic Conv-QA, 2. Single-turn QA datasets, and 3. All of the SFT datasets from Stage 1. We use a similar template as in Stage 1 to unify all single-turn QA and conversational QA datasets. In conversational QA tasks, when a document is too long to feed directly into LLMs, a retriever that can handle conversational queries becomes essential. This retriever takes the dialogue history and current query, and retrieves relevant context from documents. However, current state-of-the-art retrievers, like Dragon, are optimized for single-turn queries, which limits their ability to handle multi-turn conversational queries. To address this, we propose fine-tuning a single-turn retriever using conversational query and context pairs. Another solution is to rewrite the current question based on the conversational history, and then use this rewritten query as the input to a single-turn query retriever. To create a high-quality fine-tuning dataset, we use the conversational QA dataset from either the human annotated Conv-QA or the synthetic Conv-QA to construct conversational query and context pairs. For the human annotated Conv-QA, we directly take the annotations of the conversational query and context pairs, and use them to further fine-tune a single-turn query retriever. For the synthetic Conv-QA, we divide each document in the conversational QA dataset into different sections, calculate the 4-gram recall score between the agent's answer and each section, and consider the section with the highest recall score as the gold section for the current user's question. These conversational query and context pairs are then used to fine-tune a single-turn query retriever. Section summary. The authors generated a synthetic conversational QA dataset using GPT-3.5 Turbo and collected 7K documents from Common Crawl to generate multi-turn QA dialogues. They also constructed unanswerable samples by removing chunks of the document that had high overlaps with the agent's answer. In the training blends, they included various datasets to enhance the model's QA capability, including ChatQA for tabular documents and arithmetic calculation, as well as contextualized single-turn QA datasets. To handle lengthy documents in conversational QA tasks, they proposed a retriever that encodes dialogue history and current query to retrieve relevant context from documents. They also explored fine-tuning the retriever using conversational query and context pairs from the human annotated Conv-QA or synthetic Conv-QA datasets. Section. Conversational query rewriting. We're developing a robust model for rewriting conversational queries, and we're using GPT-3.5 Turbo for this task. This model has shown impressive results in query rewriting. To improve the quality of the rewritten queries, we provide the model with a task instruction and a few examples of rewritten queries. You can find more details in the appendix. We compared our query rewriting and fine-tuning methods across 5 different datasets. We conducted these experiments using 2 retrieval models, Dragon, a state-of-the-art model, and E5 unsupervised, a strong model that hasn't been fine-tuned on the MS macro dataset. Our findings showed that fine-tuning was slightly less effective than query rewriting in terms of average top 1 recall, but it performed better in terms of average TOP5 recall. This suggests that fine-tuning is a viable approach for conversational retrieval. Interestingly, we found that fine-tuning performed significantly better than rewriting on the E5 unsupervised model. We think this might be because E5 unsupervised doesn't use human annotated query and context pairs during the pre-training stage, which could limit its ability to generalize to high-quality rewritten queries. However, when we fine-tuned E5 unsupervised using a high-quality dataset, we saw significant improvement in both average top 1 and TOP5 recall scores. While the rewriting method requires additional computational time and potentially API costs for using powerful models like GPT-3.5 Turbo, our proposed multi-turn fine-tuning method avoids these issues. For the question answering evaluations across the 5 datasets, we consistently use the TOP5 results retrieved from the fine-tuning approach for all the QA models. More results on comparisons between rewriting and fine-tuning methods can be found in the appendix. In terms of our experimental setup, we tested different model sizes. We compared our model against several others, including Llama 2 SFT 7B, 13B, 70B, Llama 2 Chat 7B, 13B, 70B, and our in-house GPT-8B foundation model. We also compared our model against 2 strong OpenAI models, GPT-3.5 Turbo, 4K, and GPT-4, 8K. For a fair comparison, we used the same context as inputs for both our models and the baselines. We collected 5 conversational QA datasets with long documents that couldn't be directly fitted into language models with a sequence length of 4K tokens. So, we used a multi-turn retriever to get the top 5 relevant chunks as inputs. These datasets covered a range of topics and had varying document lengths. For some datasets, we segmented documents into approximately 300 word chunks and retrieved the top 5 relevant chunks as context for each user question. For others, we followed their original segmentation, resulting in smaller chunks, and retrieved the top 20 chunks to obtain a similar context length to the first 3 datasets. Section Summary. The paper discusses the use of GPT-3.5 Turbo as a powerful conversational query rewriting model, which is compared to fine-tuning methods on different datasets. The results show that fine-tuning performs slightly worse than query rewriting in terms of average top 1 recall but achieves better results in average TOP5 recall, demonstrating the effectiveness of the fine-tuning approach for conversational retrieval. Additionally, the paper presents details of the experimental setup, including the comparison of different model sizes and the collection of 5 conversational QA datasets with long documents. Section: Short Document Datasets. We've gathered 5 conversational question and answer (QA) datasets with short documents, each containing less than 1,500 words. On average, a single word is broken down into 1.5 tokens, allowing the document to fit directly into large language models, LLMs, with a sequence length of 4,000 tokens. The first dataset, COQA, is based on dialogues that are rooted in short passages. The answers are typically brief, and the passages span a variety of areas such as children's stories, literature, school exams, news, and Wikipedia. The second dataset, DOQA, focuses on 3 areas: cooking, travel, and movies. It's collected from active Stack Exchange forums and includes cases where answers can't be found within the provided document. The third dataset, CON-V-Fin-QA, is centered around the financial domain. Each document in this dataset contains a single financial report table and related text. This dataset involves arithmetic calculations and complex numerical reasoning. The fourth dataset, SQA, is based on documents that only contain a single table without any surrounding text. These documents are collected from Wikipedia, and the questions require a model with a strong table comprehension ability to provide correct answers. The fifth dataset, Hybrid Dial, is a conversational QA dataset based on documents containing both Wikipedia tabular and textual data. The questions are complex and require reasoning over the documents. Out of all 10 datasets, Conv-Fin QA, SQA, and Hybrid Dial datasets contain tabular data, while the rest are text only. To evaluate the models, we use the F1 score, a common metric for assessing QA models, for all datasets except for Conv-Fin QA. For Conv-Fin QA, we use the exact match metric because the answers involve extracting numbers from documents and performing arithmetic calculations. The answer is only valid if it exactly matches the correct answer. We also conduct human evaluations to assess the accuracy of the answers generated by our best model and GPT-4. Our ChatQA method significantly improves the model's conversational QA capability. On average, our Llama 2 chat models slightly outperform the SFT models, while our ChatQA models show around or over a 10-point absolute improvement over SFT and chat models. For instance, ChatQA 13b improves on Llama 2 to 13b SFT and Llama 2 to 13b chat by 13.17 and 10.52 points, respectively. This is because context-enhanced instruction fine-tuning allows the model to learn how to effectively extract useful information from the retrieved or relevant context. Compared to OpenAI models, our best model, ChatQA 70b, surpasses GPT 3.5 Turbo by 3.77 average points and slightly outperforms GPT-4 by 0.24 average points. We also found that the first stage of SFT is crucial for enhancing the instruction following capability of ChatQA. Removing this stage results in a 1.9-point drop in the average score. Finally, we found that incorporating single-turn QA datasets in the training blends generally improves the scores across all benchmark datasets, leading to an average improvement of 1.83 points. This suggests that adding single-turn datasets enhances the model's ability to extract answers from context, resulting in better scores in conversational QA datasets. Section Summary. The paper discusses the collection of 5 conversational QA datasets with short documents, including COQA, DOQA, Conv-Fin QA, SQA, and Hybrid Dial. Evaluation metrics such as F1 score and exact match are used to assess the performance of the models on these datasets. The results show that the ChatQA method significantly improves the model's conversational QA capability, outperforming both OpenAI models and previous versions of the model. The importance of Stage 1 SFT, supervised fine-tuning, and the effectiveness of single-turn QA datasets in enhancing the model's multi-turn QA capability are also highlighted. Section: Human Annotated Data versus GPT 3.5 Turbo Synthetic Data. We're comparing our ChatQA models using 2 different datasets. One is a synthetic dataset created by GPT 3.5 Turbo, Synthetic Conv-QA, and the other is a dataset we collected ourselves, annotated by humans, Human Annotated Conv-QA. Both datasets, each containing 7,000 entries, yielded similar average scores. This suggests that we don't necessarily need synthetic data from OpenAI models to build top-notch conversational QA models. However, we noticed that using human annotated data led to significant improvements on the QAC and DOQA datasets. This is likely because the human annotated data is of higher quality when it comes to unanswerable cases, which are present in the QAC and DOQA datasets. This led to overall improvements on these 2 datasets. More detailed results and analyses on unanswerable cases can be found in section. While F1 scores are commonly used to evaluate the quality of QA models, they're not perfect because there are often multiple ways to answer questions. So, we also used human evaluations to compare our ChatQA 70b with GPT-4. We asked annotators to check the facts in the outputs of ChatQA 70b and GPT-4 and decide which model provided a more accurate response. The results showed that our ChatQA70B and GPT-4 were tied most of the time, 69.09%, with GPT-4 having a slightly higher win rate, around 3.3%. This confirms that our model is quite capable of producing correct answers. Our model performed slightly better than GPT-4 in the Conv-Fin QA dataset, indicating its strong arithmetic calculation ability. However, GPT-4 performed significantly better in the SQA task, suggesting that there's still a gap between our model and GPT-4 when it comes to tabular reasoning tasks. We also compared our models with OpenAI models across different types of datasets in our conversational QA benchmarks. Our ChatQA70B performed better in text-only documents, demonstrating its superior text understanding ability. However, GPT-4 showed better QA capability in tabular data. For datasets that required or didn't require retrieval, ChatQA70B and GPT-4 were comparable, with gaps within an average score of 1. Our ChatQA13B showed better tabular QA capability and performed better in datasets where documents didn't need retrieval. It was on par with GPT 3.5 Turbo in text-only documents and documents that needed retrieval. For the second stage of instruction tuning, we used all the datasets where the context was provided as continuous paragraphs or documents containing the answer. However, the model needs to handle the top K retrieved chunks at inference for long documents. To reduce this mismatch, we experimented with replacing some continuous paragraphs with retrieved top K chunks to enhance the model's robustness. We used the narrative QA dataset for this study. We cut the long document into 300-word chunks and used the Dragon Retriever to retrieve the top 4 chunks as additional context. We then took these 4 chunks and the summary of the long document as the top 5 chunks. We found that using these top 5 chunks as context for training improved performance on datasets that needed retrieval but decreased performance on non-retrieval datasets. Overall, the two models performed comparably. We believe more future work can be done to find the right balance between incorporating continuous context and top K retrieved chunks in the second stage of tuning. Section Summary. The comparison between human annotated data and synthetic data from OpenAI models shows that both achieve similar results in terms of average scores, indicating that relying solely on synthetic data is not necessary for building state-of-the-art conversational QA models. However, using human annotated data leads to significant improvements on certain datasets, particularly in cases where unanswerable questions are present. Human evaluations further confirm the strong performance of our model, with slight differences observed in specific tasks such as arithmetic calculations and tabular reasoning. Fine-grained analyses reveal that our model excels in text understanding, while OpenAI models perform better in tabular data. Incorporating retrieved top K chunks during training enhances the model's performance on retrieval-based datasets but may lead to suboptimal results on non-retrieval datasets, suggesting the need for further research on balancing continuous context and retrieved chunks in training. Section. Ablation studies for inference stage. We've conducted a series of tests to understand how different factors affect the results of conversational question answering, QA. Firstly, we looked at how the number of context chunks retrieved influences the results. We found that using more context doesn't always lead to better results. For instance, using the top 5 contexts gave us better results than using either the top 3 or top 10. This is because while more contexts increase the chances of finding the correct answer, too many can lead to confusion and make it harder to extract the right answer. Next, we examined how the order of the top 5 contexts affects the results. We compared a sequential order, from first to fifth context, a reverse order, from fifth to first, a swing order, where the most relevant context is placed at the beginning and end, and a random order. We found that the sequential order was just as effective as the reverse and swing orders, while the random order was slightly less effective. This suggests that our model is good at finding the correct answer in long contexts, regardless of where the answer is located. We also found that using a fine-tuned version of the Dragon Retriever, as opposed to the original non-fine-tuned version, improved the average score. This was particularly noticeable in the INSCIT dataset, where the score dropped significantly when we used the non-fine-tuned version. This suggests that improving the quality of retrieval can directly enhance the performance of question answering. We also evaluated the model's ability to determine whether a question can be answered with the given context. We used the QAC and DOQA datasets, which include unanswerable cases, for this evaluation. We considered it correct if the model indicated that a question couldn't be answered in an unanswerable case, and if it provided an answer in an answerable case. We then calculated the average accuracy score for unanswerable and answerable cases as our final metric. When we compared our models with OpenAI models, we found that using human-annotated Conv-QA significantly increased the average accuracies on both QAC and DOQA. This is because the annotations for unanswerable cases are of higher quality in human-annotated data. We also found that our best model performed significantly better than GPT-3.5 Turbo, but was slightly behind GPT-4. Interestingly, we found that models that were more accurate with unanswerable samples tended to be less accurate with answerable samples, and vice versa. This suggests that a model that is more aggressive and provides somewhat relevant answers to unanswerable questions can boost accuracy for answerable cases, but reduce accuracy for unanswerable ones. Conversely, a more conservative model that strictly checks if a question can be answered will have the opposite effect. Finally, we found that using a small number of unanswerable samples in human-annotated Conv-QA could achieve impressive results on the unanswerable evaluation, as well as the overall conversational QA score. However, adding more unanswerable samples didn't necessarily lead to higher accuracy scores in the unanswerable evaluation. Section Summary. In this section, the authors conducted ablation studies to investigate the impact of different factors on conversational question answering, QA, results. They found that using more contexts as inputs does not always improve the results, and using the top 5 contexts yielded better results compared to using either top 3 or top 10 contexts. Additionally, they observed that the quality of retrieval directly enhances the performance of question answering, as replacing the fine-tuned Dragon Retriever with the original non-fine-tuned Dragon Retriever resulted in a drop in average score. Section: Case Study. Let's delve into a case study. We'll examine 4 instances where we compared the responses of 2 models, ChatQA 70B and GPT-4, as shown in a table. The first scenario involves a straightforward query about a board hearing. Both models were able to provide the correct answer, demonstrating their ability to handle simple information-seeking tasks. In the second scenario, the question was about a character named Arya. Here, the model had to infer information that wasn't explicitly stated. We've highlighted this in blue. GPT-4 took a cautious approach, stating that the context didn't provide a clear answer about Arya's age. This response was also accurate. The third and fourth scenarios required the models to demonstrate a solid understanding of tables and the ability to reason. In the third scenario, which was about a place called Massif, ChatQA 70B correctly compared the size of the preserved area to 3,100 hectares and provided the right answer. However, GPT-4 wasn't able to do this. In the final scenario, which was about a person named John B. England, ChatQA 70B correctly identified 3 dates but missed one. On the other hand, GPT-4 was able to correctly answer the question. In summary, these examples illustrate the strengths and weaknesses of each model in different contexts.